Aiming for distinction from carbon University of Technology and Science, Coimbatore, based from Anna University, India. He is currently working as professor in the Department of Electronics Communication Engineering at Budhiyama Engineering College, Rasipuram, Namakkal district, Tamil Nadu. His research interests is artificial intelligence with applications in image, video processing, biomedical engineering, communications, and control systems. He has over 133 research publications in international and national journals, conference books, and book chapters. He has authored 8 engineering books: Communication Engineering, Linear Integrated Circuit, Digital Communications, Digital Image Processing, Control System, FAQs in Analog and Digital Signals, FAQs in Control System, and FAQs in Linear Integrated Circuits. He has published 3 edited books as chief editor under Deepthi Press, one book from IGA Global Publisher, and one from Apple Academy. He has received a grant of for 2 of his patents and has submitted and published 9 others. He has guided 10 research scholars and 10 more are pursuing under his guidance at the university. He has also been a reviewer for Springer, Elsevier, and InterScience publishers. He has received the Distinguished Faculty Award from the Venus International Foundation, Chennai. He has visited Malaysia, Singapore, recording the Tech Talk in microchip patch antennas for 5G applications, and also visited the Material Science Lab at the National University of Singapore. We are privileged to introduce our research person. Now, this session will be taken by
Sir, you can share your screen.
Screenshot. Title of this work: Design and Implementation of Metamaterial Based Beamforming Network for Millimeter Wave Applications. This is the one emerging trend in metamaterial nowadays. Is a in antenna domain mainly used for metamaterial. Disturb metamaterial. Okay. Madam, 1 minute, madam. Madam, is okay, madam?
Yes,
Hello?
sir. Okay. Okay, sir.
Okay. This is my title of this. This is my key points of the work. That is overview, research justification, design and implementation of a microwave component for beamforming network. Beamforming. Today is now is a emerging trend beamforming network. Next, integrated 4x4 butterlet matrix for beamforming network. Next, conclusion and future work. This is my research justification. Actually, the butter matrix beamforming network mainly used for the 5G applications. 5G advantage: high speed and low latency connectivity. It is the first advantage. Next, the number of smartphone users has increased. This is the main why you are going to be forming. This is just justification. First, you start with the research. First, you need for justification. Third one is the most of must be less bandwidth available for everyone, which result in slower service. So for more lost connections. So you smartphone today number of smartphone will be increases now. So network congestion is there. To avoid the network congestion, we are using for the 5G. You are going to 5G application, 5G communication. In future, 6G, 7G, everything also will become. This is the research justification for growth increasing it will be increased gradually. It will be increases gradually for the number of statistics of this it's 1G to 5G level. This is microwave component. This is the our spectrum band. Spectrum band of the this is a microwave component. That is for 10 power minus 2 millimeter wave applications. Wavelength, key frequency. This is gigahertz. It will be working gigahertz in multimedia. I will enhance the bandwidth by simply sending a signal on completely new frequency known as millimeter wave in one of the method to overcome the issue. So presently we are going to millimeter wave applications. Next, millimeter wave is therefore is suitable for choice because of vast bandwidth. The bandwidth will be increases now. Then only we are going to millimeter wave communication. Now we are prepared. In this millimeter wave application only, we are using for this beamforming network. We are going to beamforming network. Okay? But before going to beamforming network, construct the butterlet matrix. This is the birth of the beamforming. First, higher data rate, unable to new spectrum, millimeter wave application. Next, low contingency. This is the research methodology. First, data rate today is increases gradually. So then only you are going to new spectrum. We are going to new spectrum. So afterwards, then one millimeter wave applications. Finally, we are going to low contingency. This is the driving force of the research. This is a first a beam, first a brief emphasis, less convergence. Next to the increase. Finally, it is this is my driving force of the research. Gradually, it will be increases. They reduce the data traffic and provide access to numerous 5G subscribers. The effort intend to metamaterial. Metamaterial. We are going to metamaterial applications. That is but butterlet matrix beamforming network. Then only the contingency to reduce the network contingency we are using for the beamforming network. We are using this one. Next, this is objective. First objective to use SIW substrate integrated wavelet technology to build a compact metamaterial hybrid complex for the KA band. KU band. First only we are designing the instead of microstrip, we are using for the waveguide only. We are using for this one. Everybody you know waveguide. Next to create use metamaterial based butter for CR splitting resonator. Complementary split hybrid coupler to CSRR is loaded crossover and 4 phase shifters. One butterlet matrix. Now this is a main component. என்ன சொல்றது மேடம் இதுக்கு visible madam?
Yes, sir. Visible, sir.
4 see a complementary splitting resonator, hybrid coupler, 2 CSR loaded crossover splitting 4 phase shifters are combined. This is the 4x4 butterlet matrix beamforming network. Finally, the phase we are analyzing S parameter. In antenna, we are going to S parameter, VSWR, phase shifter, beam angle, everything we are performance matrices. We are computed. So, first objective is substrate integrated waveguide. This is the new technology for metamaterial application. This is the structure of our solutions. structure of this I will first design SIW. Next அப்புறமே SIW to modification. First do for modify SIW. That objective I will do for flow chart. I will design for the flow chart of my objective of the work. First phase 1 design a sieve microwave common for beam forming network. Beam forming network. This is first substrate integral wavelet. Next I have design hybrid coupler. Next I have design crossover. Next complement after design a crossover confirmation of phase shifter. This is my workflow. First we are design the substrate integrate. First we are design. Next hybrid coupler crossover for third phase, and fourth phase I will design the phase shifter. The implement of the compact metamaterial hybrid coupler using substrate integrated waveguide technology. First technology number we are introduced. Substrate integrated waveguide technology. Actually, what is substrate integrated waveguide technology? This is a micro. This is first one is micro technology. Next is substrate integrated technology. Next advantage easy to integrate it and fabricate planar. It will be easy. The substrate integrated is a easy one. Next one disadvantage more losses. Losses will be occurs. More losses will be occurs in this one. Next reduction in losses planar easy to integrate. Wider bandwidth. Advantage also is that if you design one proposed system, you are having some advantages, some disadvantages. This is the waveguide. Everybody you know. This is the microstrip patch antenna. After the waveguide to form a make a holes. That is called to form a number of holes. Waveguide antenna. Actually, what is sieve? High performance, high yield, low cost, mass produced microwave and millimeter wave technology are to create success of commercial RF broadband. In commercial RF that is used for the this type of the antenna. This type of the design using for metamaterial. First one, waveguide to form a walls. Next, this is the structure. First one is substrate. Next one is conductor. After conductor to make a substrate. Again to make a one conductor. This is the via. This is the top view of this one. This is top view. The top view to make a hole. This is a waveguide to make a holes from this one. This is top view. This one the width diameter of the holes and diameter of the spacing between these two holes. This is a design spacing between these two waves. Finally, simulated using CST software, simulate the metamaterial to form a taper. Previous slide previous slide. A square shape is there. Square, it's a rectangular shape. Then to form a network, to form a correct the optimizer you need for optimizer result we are using for the taper will be formed. Taper will be formed. This is taper. This is a taper of this our result. This is a design parameter, patch, the size of the patch, width in millimeter, length, height, diameter. This is a substrate integrated antenna. Next, length of the microstrip, microstrip length, width of the next length of the taper length we are designed. Next, width of the taper. Why you are doing for tap? Side tone is there. Width of the taper is there. The taper is a very important. No, based on the this is optimization. First square. First make a square rectangle. Then to form a taper. Based
I
upon the
have one
taper
doubt.
only to need for the correct result. So this is my design parameter of the substrate integrated waveguide antenna. This is first S parameter, everybody know. S parameter of this one. Next BSWR is a very good result from BSWR, and the S parameter everything will be obtained for in our proposed research. This is the surface current distribution of our designed proposed antenna. What is the metamaterial? First phase we are designing the substrate integrated wave. First our designed. Metamaterial have become widely utilized for microwave application over the few decades due to ability to enhance isolation. These are main metamaterial. Decreasing losses, enable minimalization, customized electromagnetic property, offer design flexibility. You need for design flexibility ki actually metamaterial is not a separate material. This property it will be this property it will obey that material is called metamaterial. But based on the literature only we are collected. Metamaterial is not a separate any material. That any material you come using this property that is called a metamaterial. The in this work we have for complementary splitting resonator can various shape. As a resonator also is there in microwave lab. In our microwave lab, CSRR is there. Complementary split resonator having various shape including circular, rectangular, triangular, different shape, diamond shape, different shape will be there. This is the CSR structure equivalent to circuit model. This is obtained from the CST tool. Next, this first phase over, second phase 3 dB hybrid coupler. This is the coupler, structure of the hybrid coupler. Is a two input port. And is a two port network, no? Two port network, everybody two port network. Two port na four terminal is there. Input enters the current in input side and output. Transistor is a two port network. And FET is a two port network. So input is slotted. இது வந்து அவுட்புட் போர்ட். அவுட்புட் போர்ட்ல -3 0 dBல with respect input இங்க input கொடுத்து you got output. நம்ம எப்படி வேணாலும் you changing this one. Input one side you giving, you got output from other side. இது ஒன்று 0 டிகிரியில் ஒரு phase shift and 90 டிகிரியில் is another phase shift. That is the 3 dB coupler. The hybrid coupler primary job tool distribute power distribute பண்ணோம் evenly between complete port and two output port. Complete two output portuக்கு power will be distributed. Next, the power must be reach the isolation port. Power வந்து isolation portuக்கு it will be reach ஆகும் and no power must reflect back to the same input port. That is a very important one. Input power not reflect to the output. That you know about maximum power transfer theorem. Maximum power will be transferred. No reflect. No reflect from input power reflect, output power reflect to the input. That is called a property of the hybrid coupler. Hybrid coupler. Next, structure of the hybrid coupler. This is structure. I will if this is a conduct substrate layer to make a different holes. Yeah, 3 rows. 3 rows. I will equal number of holes I will design is port 1. Port 1. This is the mathematical loaded. This is port 1. இங்க பாருங்க. This is இது port 1. This is the corresponding power will be delivered. This one. The power will be equally splitted. Equally splitted. Input power. This is the already I have designed tapper hybrid coupler. Already I will already I will design the substrate integral waveguide antenna. I will compile to the metamaterial loaded to the metamaterial. This coupler also loaded with the sieve surface integral waveguide antenna. It will be loaded. The complete structure of the port 1, port 2, port 3, port 4. Power come this இங்கிருந்து இங்க போலாம். இங்கிருந்து equally split both of them. Power will be split equally in all two input port to output port. This structure is sieve with hybrid coupler. CSRR, complementary split ring resonator. Both are combined together in this space. The order to improve the performance of the traditional sieve hybrid coupler. இப்போ வந்து improve ஆகும். This is you are using this CSR with SW, no? It will improve the result. The circular CSRR was selected for metamaterial. I will select for different shape is there. I will explain previously, but in our work we are using for the circular shape. The single ring SSR construction was taken into consideration for single double ring as a single we are using double ring CSRR. We will do it. This is the performance already. Already you know S parameters. For port 1 is excited, S parameter port 2 excited, third one is VSWR, fourth one is phase shift. So here phase shift also obtained. In previous one, no phase shift will be there, but here phase shift also we are obtained. Power phase shift, different phase, only 0 degree and 90 degree phase shift will be obtained. But இதில் வந்து in previous SIW no phase shift will be there. So input port transfer to output, but in this one our SIW with CSRR I will load it, so power will be splitted. That is the performance analysis of this our one. This is our this is the comparative with CSI with SIW what happened. SIW what happened? SIW with the CSRR what happened? Both are is the performance hybrid coupler. S1 parameter, SW1 parameter, everything will be, I will introduce here. Next. Madam, the audible, no? Hello? Hello? Next. Design a metamaterial. Madam, audible? The design metamaterial basis complementary patient.
Yes, sir, audible.
Next, so part two, one objective is completed. To one objective. First one, design SIW with CSR loaded antenna. I will design. Next, design metamaterial based complementary phase shifter. Now we are doing for complementary phase shifter metamaterial. This is complementary phase shifter. This is in port A. The isolated port A. is port A, for input port B. The single channel must physically cross over into the butter matrix with a preservation eye isolation. This may be demonstrated using normal hybrid. First, we have demonstrated normal hybrid analysis. Why you are using crossover? First, why you are choosing crossover? No, the power will be splitted. No, the power will be crossover will be occurs. So, to avoid the crossover, to design the one crossover network now. Crossover. Next, it is possible to establish strong isolation between two crossing signals. So, no, the strong, mainly, hello, strong isolation. You need for strong isolation. If isolation is not strong, no, so crossover will be occurs. So design the next case crossover network. Crossover parameter. This is structure of the SIW with the CSR loaded and a crossover. This is the crossover structure. This is the crossover. The structure of the crossover. Crossover of this antenna. Crossover. Now we are simulating structure of the crossover. So here this SIW with the CSRR and the crossover. This is the performance analysis. Crossover. S11 parameter used by S11 parameter, transmission coefficient, and the phase shifter. Used for this one. Next, this is the phase shifter. Next, corresponding phase shifter. Structure of the SIW corresponding phase shifter. This is the phase shifter. One is 180-degree phase shifter. 180-degree phase shifter. This is everything I will design for the CST tools. 60-degree, 180-degree, different phase shift will be obtained. Different phase shift. 135. This is the complete structure. Phase shifter of number I use for the 45-degree phase shifter. Port 1. Input port 1, 2, 3, 8 port will be there. 8 port. So input transfer from one port, you take the output to different port with any no crossover be occurs. Without any crossover, input transfer to the output port. This is the result analysis of the phase shifter. 45-degree. For 45-degree, it will be analysis of the phase shifter result. There is a reflection and transmission coefficient of 40-degree phase shifter. First A. Next one, the reflection and transmission coefficient 0-degree phase shift. There is a diagram B. C வந்து VSWR. இது வந்து 0-degree உள்ள VSWR. But everything, the performance will be very nice in our design of the structure. This is the integration of 4. I will combine all phase shifter, crossover, SIW, and CRR, complementary splitting. I will combine everything. We are combined, put together to construct to design a one buttered matrix. Next, integration of 4x4 buttered matrix from microwave component. Integration. Now, this is the buttered matrix component view. This is a complete view. I will design all component to represent this diagram. Complete all structure. SIW, CRR, phase shifter, and crossover. Everything is put together. That is called Butler matrix. Butler matrix concept view. This is Butler matrix concept view. This is a port 1. This is port 2. Port 3. port 4. This is a different beam. First பாருங்க for 490-degree hybrid couplers make up a 4x4 Butler matrix. So 490-degree hybrid coupler, 2 crossover and phase shifter. This is called one 4x4 Butler matrix modules. Port 1, 4 are loaded in input port. 1 and 2 for input port. 5 and 2 are designed to the output port. Number that we are designed. 1 to 4 is the input port. 5 and 8 is the output port. The phase difference that form between the adjacent output port when the signals are transmitted from port 1, 2, 3, 4 and a signal we are transmitting 4 to 1, 2, 3, 4 in a conventional beam is shown in the figure. Yeah, 45-degree, 135, minus 135, plus 45. Different phase to transmit the signals from different phase. We are transmit the signals from different phase. This is the phase difference between this table. This is my complete product of this one, Butler matrix. The Butler matrix consists of crossover, phase shifter, and CRR and SIW. They combine together to form a 4x4 Butler matrix antenna. Not a antenna. After beam forming, first design a beam forming. After beam forming, next I will insert the antenna from this Butler matrix. So in the antenna will be now still now we are not interface with the antenna. In future we are interface the antenna and we are analyze the performance of the antenna. So if I design the antenna now, I will test for the radiation pattern. Now I will not concentrate radiation pattern. Now we are designed only for the beam formation only. We are designed only. After beam formation, to the antenna will be integrated now to give a one. It's a one of the product. There are 4x4 Butler matrix, 8x8 Butler matrix. Different type of Butler matrix also is there. We are different type of antenna. We are used for test this Butler matrix. Next, performance analysis of 4x4 Butler matrix. This is a performance analysis. First, anyway, return loss. Analysis return loss. Next, return loss from port 1 excitation. Port 1, I will give the excitation. Suppose input, I will give the port 1, no. I will calculate the return loss from the input port. Next, isolation port 1 excitation. What is isolation also I will measure. Third one, transmission coefficient. Upper phase shift. Port 1, I will similarly port 2. All the parameter analysis port 2. Similarly, VSWR. Next one is surface current distribution. Everything I will measure. Here I will see, compare this one. Port 1, sorry, transmission is a port 5, 1, port 5, port 4, port 7. Everything input port and output port. Everything I will calculate the transmission reflection coefficients. The objective of this work to implement small 4x4 beamforming method to millimeter wave frequency. Spectrum using SIW antenna. Initially an integrated waveguide. First waveguide, I will first I will start the waveguide. Are jointed and the SIW are jointed to form a standard hybrid coupler that is called the phase shift of the output port is 90 degree number first I will design 90-degree apart and divided power equally. Next, limitation of the traditional hybrid couplers such as their small bandwidth and bulk size. Yes, sir. Bulks were lessened by the adding the complementary splittering. I will use it for the complementary splittering. I will use it for this one. Next, because of the return loss less than, this is our result performance less than 10 dB between 90 gigahertz per 40 gigahertz. The CSR, if you suppose I loaded the CSR now, up that is overall it only reduces to 10 is to 10 into, this is the size of this one. Our bandwidth also increases 10 gigahertz. 10 gigahertz. Must is changing the SIW with the phase shifter or implemented. Standard SIW2 hybrid couplers are added to create crossover. Finally, building component with the complex comprised phase shifter, crossover, and hybrid couplers are integrated to generate the 4 SIW Butler matrix. And then finally, I will estimate all the parameters also. I will calculate all the parameters. Next, in suggested small, first very small, is only practical. This is trial method only. Small forecast for Butler matrix and the overall occupation. This is the area of the occupation. Phase incurrency of roughly phase incurrency. That is the phase shift. You design 4 phase shift. We are using 8 கூட you are use பண்ணலாம். But here I use for the 4 phase shift only are used. The subject CSR loaded. இப்போ I am using for the loaded CSR. Load பண்ணும்போது Butler matrix potentially to enhance the bandwidth. Without, suppose you send the signal from SIW, but bandwidth will be reduced, not enhance the bandwidth, but to increase the bandwidth, to load at the metamaterial. Metamaterial means CSR, complementary splittering resonator. I will load it to increase the power, to increase the bandwidth. Finally, I will add the phase shifter and crossover and increase the number of ports to form a different beam will be formed and different phase. It is an advantage. Finally, I will insert the antenna. It is my final stage. This is some of the future to verify radiating beam property. 4 cos for Butler matrix can be combined with 1 cos for linear array. First, here I not insert any antenna. First, I will one antenna. I will use it for one antenna. Upon H plane complex crossover and phase shifter can be used to extend the 1D Butler matrix. H plane you are using for H plane no 1D Butler matrix. Now we are extended to 2D Butler matrix. Now we are extended 2D Butler matrix. The boost of the gain. Suppose I want now we are concentrating only gain, not I will not concentrate because I will antenna if using the antenna only to calculate the gain and radiation pattern. To boost up the gain of the directed guided beam and anti-potential Vivaldi antenna. Vivaldi antenna, that one type antenna. We are using this Butler matrix, no? Definitely gain also increase. But in future, the antenna, I will design the antenna. I will design the Vivaldi antenna. I will design the. I will publish the paper, but I will not interface with the antenna with the Butler matrix. So I will combine this. What happened the radiation pattern? How will radiate with the Butler matrix? What is the radiation pattern of the antenna? without button matrix, what is the radiation band antenna? And you are using the button matrix, beamforming will occur different direction. Finally, to record its performance real time. Forecast, so based on real time, now we are antenna, your superimpose the antenna which is matrix in real time, we are in future we are dying. This is some reference. Actually, this is a complete product. It is only a very good product. It is only இன்னும் கொஞ்சம் we are extended this work now. Definitely patent everything will approve. It will be definitely further we are going this study in future. Hello, madam. Hello. Hello.
Sir,
Madam, any doubt in the ask, madam? This work. This is one of the research work is going on. For 80% is completed, but antenna stage only is pending. Remaining beamforming and button matrix already we are completed. At the stage I will tested with the simulation result. I will tested. Antenna I will tested with the radiation chamber. Chamber we are tested with the antenna. Antenna performance also we are analyzed without button matrix. After connect this button matrix antenna, then we are further we are analyzed for radiation pattern. Then only you give the very overall product of the design structure. Anything you want to this research, just to I will interact with you.
participants, if you have any queries, you can ask sir, or you can post your queries in the chat box. Sir, if you want to work any collaboration work, can we join with you in this
Sure,
work?
okay, madam, but you'll do it.
Sir, give me your contact mail ID. So that if anybody wants to join,
you note it, no? Actually,
participants,
you want
you
to
can post your
collaborate,
queries in the chat box. Sir?
Chamber also is there.
Okay, sir. In your college, you have anechoic chamber facilities.
Anakia chamber also is there.
Okay, sir. If you want to test the antennas, can we request and test our antennas in your institute?
In our institute is not there, madam.
Okay.
But my one lab is there in Chennai.
Okay, sir.
Chennai. The lab we will test anything, madam.
Okay.
Yes. Lab one my students also is working one of the company, antenna design industry. She is working in US based company. She is completed PhD in this area. Now we are started with one startup with antenna company. In research studio, we have started one company in antenna design. Already we are designed around 70 years. Already we are first home screen. So already over 50-60 antenna we are designed, madam. Different is now we are going to in this one. Now we are started with one startup of this PCB.
Okay, sir. Very nice presentation, and thank you for sharing the information. If you want to collaborate in future, we will contact you. And about the surface wave integrated technology, and is useful in millimeter wave antenna design and 5G, 6G communication and antenna miniaturization. Your concepts are very useful. Thank you for your nice presentation. Thank you, sir.
Thank you, madam. But we are having many work also is there, madam. If you want to design antenna, Anaki chamber, some low cost is available in Chennai. Low cost Anaki chamber also is there. You want to design any antenna in chamber, no, we will do it. But we are doing many pattern work also in this area.
Okay, sir.
Okay,
Thank you.
madam.
We will be contacting you in future regarding this collaborations. Share your email ID in the chat box, sir, so that participants can know.
Chat box, I don't know. But I will note it. Ganesh Babu, my name, GANESK. Ganesh Babu, tr@gmail.com.
Okay.
Ganesh Babu, tr. Okay.
Okay, sir.
So this is the combination of transmitter side as well as the receiver side. Okay. So we'll see what is the transmitter, how to design and how to architect this one. So in this session, we are going to discuss about receiver architectures as well as transmitter architectures and transceiver design issues. Okay, in case of receiver architectures, there are 4 types. That is homodyne, heterodyne, image reject, as well as low intermediate frequency. In case of transmitter architectures, direct up conversion, 2-step up conversion. And part 2, we are going to discuss about the transceiver design issues, noise figure, total harmonic distortion, second order intellectual points, third order intellectual points, sensitivity, SFDR, as well as phase noise. This is the left hand side shows the transmitter side and the right hand side shows the receiver side. So while transmitting the channel, it has to pass through the medium or passing the data. It has to go to the transmitter side and then it has to pass through the channel. The channel may be affected by the noise, and while at the receiving side, we have to retrieve that carrier signal as well as the original signal, and it has to be passed to the receiver side. Okay. So this will be the transmission line. So transmitter side, transmission line. So here there will be transmitting antenna, and it has to be transmitted through antenna pattern, and it will goes to the wave polarization as well as the air medium. And at the receiver side, we are having the receiver antenna. So we can see SWR, and this will be the receiving antenna pattern. And this will be the transmitting antenna pattern, and this one will be the receiving antenna pattern. So it has to pass through the receiver. Okay. So the distance between a transmitter and a receiver will be R. So in wireless world, most of this we are using nowadays. So mostly laptops we are using, cell phones we are using, camcorders, digital cameras, microwave ovens, TVs, printers. Okay. So high-speed wireless links, that is Wi-Fi and Bluetooth, allows seamless connection among devices and appliances. Okay. So importance, why we are discussing this one means in our field, wireless system designs draws upon a multitude of disciplines. So CAD tools, IC design, transceiver architectures, random signals, communication theory, microwave theory, signal propagation, multiple access, and RF design. Okay. So in my during my studies during the ME time, so I have done the simulation for this one using the cadence, as well as for cadence I have drawn the layout, and for a simulation purpose I using TCAD as well as Agilent tools we are using for the simulation in order to detect the transmitting power and the noise figure, SN, SWR. For that I have used Agilent tools. So RF wireless design is challenging. So what are the trade-offs while doing the experiments? So we may occur noise power, frequency, linearity, supply voltage, gain. So in case of linearity, we are having a DNL as well as INL. So that is a integral nonlinearity, differential nonlinearity that will comes into the effects. Okay. So this RF circuits and the transceivers must deal with numerous trade-offs. Demand for higher performance, lower cost, as well as greater functionality. So in trade-off means while we are increasing the frequency, so the power may be increased or power may be reduced, the area may be increased. So these are all the trade-offs which will comes under during the experiments. So order of communication. So transmitter, that is drive antenna with high power level. While means while transmitting the data, it has to be multiplied with the carrier frequency. So then only it will be transmitted through the medium. And at the receiver side, we have to that suppress that carrier frequency. For that, we are using low noise amplifier or a LO oscillator like that. Okay. So the receiver side sends a small signal, so amplify with low noise. So transmitter side giving the input data as voice or data, and it has to be transmitted through this transmitted antenna, and it has to pass through the medium. At the receiver side, we are having the receiver antenna, so the data has to be passed through the receiver. So we may reconstruct the original voice or data. Okay. So voice or data. So up converter modulator. So power amplifier. We have to. This will be the input signal, and it has to be up converter. For that, we are using a mixer circuit. It has to improve the. The voice of data will be having the low frequency, and it has to be multiplied with the higher frequency in order to transmit through the channel. Okay. For that, and there will be power amplifier, and this will be the carrier frequency, and this will be the frequency. Okay. The receiver side, we are having the low noise amplifier. Okay, during the transmitter side, we are having the power amplifier. Receiver side, we are having low noise amplifier, and that we have to suppress that carrier frequency. So for this, we use demodulator. So and after that, we can reconstruct the original voice data. So this is the RF communication transmitter along with the receiver. That is the transceiver. So generic or of so digital baseband processor, that is the voice or the data. So it has to be passed through the digital to analog converter, and it has to be up converter or modulator. For that, we are using the frequency synthesizer. So that carrier frequency will be multiplied with this one, and it has to pass through the power amplifier, and then it has to be transmitted through the antenna. By this antenna, we can receive the data. The received data will be passed to the low noise amplifier, and it is a down converter or demodulator, and it has to pass through the A to D, and we can reconstruct the original signal. So signals are up converter or down converter at a transmitter and receiver by an oscillator controlled by a frequency synthesizer. Next one is RF transceiver. Okay. Here that a baseband signal, that is a voice or a signal, voice or a data. So it has to be up conversion. For that mixer. Okay, there is here we are having the RF signal input data multiplied with a uh, low frequency oscillator, and we can have the up conversion mixer here. So it has to be it will be multiplied, and it has passed through the power amplifier, then RF filter, and here we are having the transmitted antenna, and this will be the transmitted pattern. So if you see upwards, there will be, this is our desired channel which we are going to be transmitted, but there will be some interference will be here will be present. Okay. And it has to be passed through this one. So at the receiver antenna, we can receive this signal, and the receiver pattern will be, antenna pattern will be like this, and it has passed through the transmission line. Here there will be RF filter. Okay. And it will eliminate the high frequency signals. Here the noise will be present. We have to suppress that one. For that, we are using the low noise amplifier, and we have to suppress the carrier frequency which is transmitted here. We have to suppress that one. For this, we are using down conversion mixture. So then we can get the intermediate frequency. So during this low noise amplifier, there will be there will be some spectrum regrowth or intermodulation. There will be some nonlinearity will be present. In order to suppress that one, we are using this low noise amplifier. Here, after passing through the down conversion, we can get the intermediate frequency, and there will be, we are having this RX receiver circuit noise. So here we are having in phase quadrature as well as in phase noise as well as quadrature. Okay. So main RF transmitter receiver or transmitter building blocks are RF switch, transmitter switch, receiver switch, RF filters, receiver low noise amplifier, receiver down conversion mixer, transmitter power amplifier, transmitter up conversion mixer, local oscillator, voltage controlled oscillator, receiver or in phase or quadrature demodulator ADC. So these are all the main building blocks in transceiver side. So general considerations, narrow channel bandwidth. Here, the data during the transmitter side, we are using this power amplifier. It has to pass through the band pass filter. Okay. So here, this is the transmitter channel. Along with there will be some adjacent channels will be present. Okay. So in this one, second one, band pass filter. Band pass filter response will be like this. This will be the desired channel. So there will be some adjacent channel, alternate adjacent channel will be there. So narrow channel bandwidth impacts the RF design of the transceiver. So channel selection and band selection. So all of the stages in the receiver chain that precede channel selection filtering must be sufficiently linear. Channel selection must be deferred to some other point where center frequency is lower and hence required Q is more reasonable. So most receiver front ends do incorporate a band select filter. Okay, most of the receiver side we are using the band pass filter in order to suppress that adjacent channel coinference like that. Okay, so that is that the band pass filter will be present before the low noise amplifier. So if you see this one, so this will be the channel. So and this will be the interference. So by passing through the low noise amplifier, we can remove the inference. So duplexer characteristics. So transmitter side we are having 50 decibel, but at the receiver side we are having the 30 decibel. Okay, so the front end band select filter suffers from a trade-off between its selectivity. Okay, so here the selectivity plays the main role. So in band loss, because the edges of the band pass frequency response can be sharpened only by increasing the order of the filter. In order to get to the high accuracy, we have to increase the order. While increasing the order, there will be some trade-off will be occurring. Okay, so front end loss directly raises the noise figure of the entire receiver. So this will be okay. So here we are having the 50 dB. Here we are having the 30 dB at the receiver. In order to retrieve the original signal, we have to increase the order. Then only the adjacent channel interference will be ejected. So transmit and receiver feed through. Okay, so here we are having the duplexer. So here with the 1 watt will be the transmitter. Okay, 1 watt transmitter power. The leakage sensitive by a low noise amplifier will be minus 20 dBm. So in full duplex standards, the transmitter and the receiver operate concurrently. So example for a transmitter receiver leakage. Okay, so consider this is the transmitter leakage. So it has to be passed through the low noise amplifier. Okay, so after passing the band pass filter, we may obtain this frequency response. Okay, so if you see that the input, so the leakage will be more. So after passing through this one, we can eliminate one. So if the band pass filter provides additional rejection in the transmitter band, the linearity required of the rest of the receiver chain is proportionally relaxed. Basic heterodyne receiver. So far we have discussed about homodyne receiver. Next we are going to discuss about heterodyne receivers. So this will be the RF input. Here heterodyne receiver. So RF signal will be mixed with the local oscillator LO. We can get the intermediate frequency. Okay, so RF input WN omega n will be the input. So local oscillator input will be A0 cos omega L0 of t. So it has to be passed through the mixer, and after that it has passed through the low pass filter. We can get the intermediate frequency. For example, consider this as the input, that is minus omega n plus omega n, and a local oscillator frequency minus omega L0 and plus omega L0. So we can obtain minus omega n minus omega L0 and minus omega n plus omega L0 plus omega n minus omega L0 plus n plus omega L0. We can get a 4 frequency signals. Okay, here. So heterodyne receiver implies an LO frequency unequal to omega n, hence a non-zero IF A mixer performing down conversion, due to its high noise, the down conversion mixer is preceded by a low noise amplifier. So basic heterodyne receivers. So similarly, this will be omega n, omega em image frequency. Here we're having omega L not local oscillator frequency. So the difference between omega intermediate frequency. So here we are having a local oscillator cos omega L naught. It has to pass through the low pass filter. Then we can have the output as omega f with omega. So a cos of omega f t is equal to a cos of omega n minus omega L naught of t. So a cos omega L naught minus omega n of t. So we can give omega image equal to omega n plus 2 omega if, which is equal to 2 omega L naught minus omega n. So two spectra located symmetrically around omega L naught are down converted to the intermediate frequency. So an example of image channels at omega n, omega 2 less than omega 2. So the down converted spectrum as the low frequency varies below omega n to above omega 2. Okay. So this is minus omega 2 minus omega n plus omega. So here omega L naught less than omega 1. So here it is omega 1 and omega 2. So here what this is the this will be the local oscillator frequency. We can add this one. Okay. So minus omega 2 minus of minus plus omega L naught will be here, and minus omega 1 plus omega L naught, then plus omega 1 minus omega L naught plus omega 2 minus omega L naught, like that. So here WL naught slightly above omega 1. So here we can obtain this one.
Okay.
So suppose two channels at omega n and omega 2 have been received, and omega 1 is less than omega 2. So the down converted spectrum as the low frequency varies from below omega 1 to omega 2. So the another example for image. So down conversion using expression for the desired signal under the image.
WhatsApp Rajesh sir our group lo personal group. Industrial visit payment details. அப்படின்னு ஒரு heading. கீழே UPID extra add பண்ணணும் already.
Is I audible now? So is I audible now?
Yes, sir.
You're audible, sir.
So is I audible now?
Yes, sir.
Okay. Here we are going to see about dual down conversion. So far in the last we have seen about in the receiver antenna we are having only one band pass filter and one low noise amplifier and one local oscillated frequency. Here we are having two dual conversions. So here we may have more band pass filter as well as a more low noise amplifier. Okay, so more band pass filter as well as more local oscillated frequency, but we are having one low noise amplifier and one IF amplifier. Okay, so here this will be the decide channel. This will be the decide channel. So here we are having this. These are the interferences, and this will be the image. Okay. So after passing through this dual conversion, so after passing first band pass filter, we can obtain this one. Okay, so this will be A, and this one will be B. Okay, so this input is passed through band pass filter one. We can get this one. Okay, so here we are suppressing this interferences here. Okay, so the front end filter selects the band while providing some image rejection as well as point B. Okay, so here if you see this, here we are having rejected this interferences. Now we can see what is the C. So the B will be after passing the B signal to the low noise amplifier as well as band pass filter. That is image reject filter. We can obtain this one. Okay, so this will be the C point. Here what we are doing means here we are suppressing the image. So here we are having the image signal. This image signal is suppressed here because we are passing the information through the image reject filter. Okay, so we can remove this image signal. Okay, after that we are having the interferences. Okay, so we can so after amplification and image reject filtering, so spectrum of C is obtained. So sufficiently linear mixer translate the desired channel and adjacent interference to first intermediate frequency point. Okay, so this will be the first intermediate frequency. We can obtain this one. Okay. And this has to be passed to the again IF mixer to channel select. We may get the G output. So E is this one output and F is this one. So partially channel selection band pass filter 3 permits the use of a second mixer with reasonable linearity, that is point E. So spectrum is translated to second intermediate frequency, that is F. Okay. So F is shown here. So for this the output is this one. Okay. So spectrum is translated to second intermediate frequency. So 0 second intermediate frequency. So consider that this is omega I1, IF1, and for this is the mixer. Okay, so one of the input L02. So we may obtain this one. So to avoid a secondary image, most modern head-end receiver employ 0 second intermediate frequency. So in this case, the image is the signal itself. Okay, image is the signal itself. No interference at other frequencies can be down converted as an image to a 0 center frequency. So that is, so what we are giving the input will be equal to the intermediate frequency. So direct conversion receivers. So here we are having the input and it has to be receiver input. It has to be passed through band pass filter, low noise amplifier. Here we are having the intermediate frequency as well as quadrature phase frequency. So that is the low noise output is multiplied with cos omega L0 in order to get the in phase. This is multiplied with the sin omega L0 in order to get the Q. Absence of image greatly simplifies the design process. Channel selection is performed by on-chip low-pass filter. So mixing spurs are considerably reduced in number. So LO leakage, that is a local oscillator leakage, will be present. Okay, that is if you see the board, there will be a receiver and it has to be passed through the pad low noise amplifier. there will be some interference will be present. And here also local oscillator and the low noise amplifier, there will be some leakage will be present. So it has to be mixed with the low oscillator frequency. The low noise amplifier output is mixed with the local oscillator. Okay. So the LO couples to the antenna through, so there is the local oscillator couples to the antenna through device capacitance. Okay, so here we are having two capacitance. One device capacitance is between the low noise amplifier, and another capacitance is between low noise amplifier as well as the local oscillator. So that is here the device capacitance between local oscillator and RF ports of mixer, and the device capacitance or resistance between ports and inputs of the low noise amplifier. The substrate to the input pad, here this is the substrate to the input pad, especially because the low oscillator implies large on-signal spiral inductors. Okay, so there will be some leakage due to capacitance as well as inductors. Obviously, if you see the two wireless transmission line, so in between there are two conductors, there will be air medium, so obviously the capacitance will be found. So like that, here also this will be two conductor air medium, so the capacitance will be found. Okay, because of this, the leakage will be. Okay, so DC offset, already you know what is meant by offset. So without giving any input, if you get some output, there will be some offset. So here in this case, there will be DC offset. So here low noise amplifier is the A point. It is be passed through low noise amplifier antenna, and the low noise amplifier output is a B. So here if you in between this low noise amplifier as well as the local oscillator, there will be LO leakage. Okay. And mixer output is cos omega L naught of t, so it has to be passed through low pass filter, and we may get the ADC. From ADC we can retrieve the original signals. Okay. This is omega RF low noise amplifier. So here it is omega L naught equal to omega RF. So this will be the DC offset point. So a finite amount of in-band low LO oscillator leakage appears at the low noise amplifier. So along with the desired signal, this component is amplified and mixed with the local oscillator. So may saturate baseband circuits, simply prohibiting the signal detection. So second intercept point. So we are moving to the second intercept point. So if Vn of t is equal to A cos omega 1 of t, A cos omega 2 of t, then the low noise output is given by so V out of t is equal to A1 Vn of t plus alpha 2 Vn square of t. So which can be written as alpha 1 A cos omega 1 of t plus cos omega 2 of t, and alpha 2 A2 square A square cos omega 1 of plus omega 2 of t plus alpha 2 A square cos omega 1 minus omega 2 of t. So this is alpha 1 into A, alpha 2 into A. So this will be the second intercept point. Okay, so this alpha 1 A is the first intercept point, and this one will be the second. So beat amplitude grows with the square of the amplitude of the input tones. So in phase quadrature mismatch. Okay. So here this receiver voltage is passed through 90-degree phase shift. Here it is directly given to the mixer. Here the mixer, another mixer input is a low. Here we are having the 90-degree, so we have in phase quadrature. In phase, here we are having the quadrature. So here in between the low, so the low noise VLO local oscillator is given as 90-degree phase shift here. So we may get I, and these are the two ones. So separation into quadrature phase can be accomplished by shifting either in the RF signal or the low F. So in the first diagram, we are shifting the RF signal. Here we are doing a 90-degree phase shift only to the local oscillator waveform by 90 degree. So errors in the 90-degree phase shift and the mismatches between quadrature mixer results in imbalance in the amplitude and the phase of the baseband I and Q outputs. So this is VR of phase and gain error. Okay. So IQ mismatching, direct conversion receivers and heterodyne topologies. So here we are having the input as 5 gigahertz. It has passed through the low noise amplifier. So we may get a delta T is equal to 10 picoseconds. So we may, in phase here, we may get the quadrature phase.
So the quadrature mismatches tend to larger in direct conversion receiver than in heterodyne topologies. So this occurs because the propagation of a higher frequency FN through quadrature mixer experiences greater mismatches. The quadrature phases of the LO itself suffer from greater mismatches at higher frequencies. So this is the effect of mismatch in phase side. So let us lump all of the gain and the phase mismatches shown below. Effect on QPSK signal. So quadrature phase safety giving signal install constellations. Okay. So x of local oscillator I of t is equal to 1 plus epsilon by 2 cos omega c of t theta by 2. Similarly, we can this one. So here x in of t is the input. So it has to be multiplied with the local oscillator before passing through the low pass filter. Okay. So here we are having 90-degree phase shift and plus theta by 2 minus theta by 2. So here we are having 1 plus epsilon by 2, 1 minus epsilon by 2. Okay. So we may get this x BB of I of t and XBB of Q of t like that, like this. So image reject receivers, mostly here you are using the Hartley architectures. So if we shift I of t or Q of t by another 90 degree, okay. So in previous side, we are shifting either the RF signal or the local oscillator signal. But here we are, if we shift the I of t or Q of t by another 90 degree before adding them, so the image may be removed. In order to remove this image, so after the low pass filter, we have to add another 90 degree. We can remove that image signal. Okay. So the low pass filters are inserted to remove the unwanted high frequency components generated by the mixers. The principal drawback of the Hartley architecture stems from its sensitivity to mismatches. So far we have in all this one, we are having the image frequency. Okay, in order to this will be the image. So we can remove this by using bandpass, but in order to remove this image one, so we have to pass another, we have to add another 90-degree phase shift, then we can remove the images. So next one is the Weaver architecture. So the Weaver receiver derived from the transmitter counterpart avoids these issues in Hartley architecture. Okay. So here RF input is passed through the mixer. One of the input is sin omega t, another one is cos omega t. We can get the low pass filter out, low pass, and it has to be passed to another local oscillator. So there is sin omega t, cos omega t. So we can, it is passed through the low pass filter, and we are having the intermediate output. So mixing a signal with the quadrature phases of an LO takes the Hilbert transform. Depicted above, the Weaver architecture replaces the 90-degree phase shift network with quadrature mixing. Okay. So low IF receivers. So it is undesirable to place the image within the signal band because the image thermal noise of the antenna, low noise amplifier, and the image stage of the RF mixer would raise the overall noise figure by approximately 3 dB. Now suppose the local frequency is placed at the edge of the desired 200 kHz channel, that is here. Okay, local oscillator frequency, this frequency is 200 kHz. So we may have 200 kHz here. Okay, so this 200 is split into 100 here. So here, if for this, we may get this adjacent channel, the 1 by F noise, the signal becomes feasible. So this is a low IF receiver for possible cases. Okay. So so far we have seen homodyne, heterodyne, image reject, as well as low IF. So these are the 4 possible building blocks: homodyne, heterodyne, and then we are having a low IF, and another one will be combination. So RF receiver advantage, RF receiver output super heterodyne. So this is advantages: reliable performance, flexible frequency band, no DC offset, and 1 by F noise. So the disadvantage, it will be expensive, as well as the power consumption will be high. So this will be difficult to share the ACW filters or multi-standard. So image reject both the outlets as the Weaver. So it high integrability. So quadrature of to be conversion suffer from first and the secondary images, narrow band, IBQ math. So 0 IF. So its advantages will be or misconstruction, high integrity, no input. Percentage will be quadrature R of 2 dB conversion, DC offset and 1 by F noise patterns. So low IF, which is a low cost, high integrability, small DC offset and 1 by F noise. So image is a problem in low IF. So quadrature R of 2 IF and double quadrature IF 2 dB. So transmitter architectures, one is a direct up conversion and another one is a two-step up conversion. So that is a spectrally efficient modulation, efficient signal amplification with power. So in a transmitter, the basic building blocks will be power amplifier and mixers, then voltage controlled oscillators and amplifiers. So in contrast to the architectures are found only few. So the transmitter output must pass through duplexer filter time division so that it can be separated from the signal received by the antenna. So duplex filters typically exhibit a loss of 2 to 3 dB, dissipating 30 to 50% of the power amplifier output power in form of heat. If the power amplifier provides 1 watt of power, more than 300 milliwatt is wasted in the filters. So these are all the transmitter issues. So direct conversion transmitters. So GMSK waveform can be generalized to any narrowband modulated signal. So X of t is equal to A of t cos omega C of t plus pi of t. So that is A of t cos omega C t omega cos of pi of t minus A of t sin omega C t sin phi t. So we therefore define the quadrature based on the signals as, so X BBI of t is one of the input and X BBQ of t is the another input. So that is X BB of t is equal to A of t cos pi of t, and the X BB of Q of t is, that is the I of t is the in phase and the Q of t is the quadrature phase. So which is A of t sin pi of t. So this topology directly of quadrature up converter. Okay. So power amplifier and it will be passed to the matching network duplexer and it will be transmitted to the antenna. So oscillator pulling. So the power amplifier, the output exhibits very large swings, which coupled to various parts of the system through silicon substrate package parasitics traces under PC. So that is it is likely that an appreciable fraction of power amplifier output couples to the So modern direct conversion transmitters. So most of today's direct conversion transmitters avoid an oscillator frequency equal to the power amplifier output frequency. So this architecture is popular for two reasons. One is
for your guidance the following family members are invited for exams. Device for the academic 2026 hours.
The divider readily provides quadrature. Suppose each circuit is equal to A1 alpha 1 A cos omega 1 of t. So this will be the derivation. We can move that the output spectrum contains a spur at 3. The output spectrum contains a spur at 3 omega 1 minus omega 2. So similarly, with the third order nonlinearity in the mixer ports sensing omega 2 of t and the sin omega of 2 of t, here the sin 2 of t and the sin omega of t. So a component at 3 omega 2 minus omega 1 will be arising at the output. So this will be the overall spectrum. So if you see here, so 3 omega 1 minus 3 omega t and the cos omega t. Okay, so will be like this. So this is omega 1 minus omega 2, 3 omega 2 minus omega 1. So omega 1 plus omega 2. So between the two spurs, 3 omega 1 minus omega 2 and 3 omega 2 minus 3 omega 1. That is 3 omega 2 minus omega 1, 3 omega 1 minus omega 2. So only one can be reduced to acceptably low levels while the other remains only at 10 dB. So this one will be increasing to 20. So remaining are maintaining at 10 dB. So heterodyne two-step transmitters. So this perform the signal upconversion in 2 steps so that the local oscillator frequency remains far from the power amplifier power spectrum. Okay. So sine in phase will be multiplied mixed with sine omega 1 of t. This Q phase is multiplied with cos omega 1 of t. So we may get this one. So as with the receiver counterpart, one advantage of this architecture is that the in-phase or quadrature phase upconversion occurs at a significantly lower frequency than a carrier. So exhibiting smaller gain and phase mismatches. So transmitter architecture, spectrodyne, direct upconversion, and the two-step advantages as well as disadvantages. In case of super heterodyne, so this will provide a reliable performance, flexible frequency plan, no LO leakage, simple DC offset cancellation at BB. So disadvantages: expensive and bulky, high power. Difficult to share the SAW filters for multi-standard. So direct means low cost, simple frequency plan for multi-standard, high integrability, no image problem. So for two-step, the advantages will be low cost, high integrability, and simple DC offset cancellation. So RF section, okay. So today's mobile phones contains more than 1 million transistors. Only a small fraction operate in the radio frequency range, the analog front end. So several order of magnitude more perform low frequency passband. So analog and digital signal. The RF section is the design bottleneck of the entire system, multidisciplinary field, complex trade-off. So RF design octagon and lack of design goals. So this will be the RF design octagon, noise, linearity, gain, supply voltage, voltage swings, speeding, output impedance, as well as power. So the receiver issues are sensitivity, selectivity, as well as quantified by tone, noise figure, distortion, and intermodulation. Blocking performance, distortion, and intermodulation. So signal processing. So here in signal processing, we are having a amplification, down conversion, modulation. Next one is the gain compression, 1 dB compression point. So 1 dB compression point in the sense the output falls below its ideal value by 1 dB at the 1 dB compression point. So peak value.
எதுக்குள்ள மேம்